Hey guys, Mr. Smith here, and in this lesson we're going to be talking about families of polynomial functions. So let's get started. As a bit of a a motivation to today's topic, consider maybe you have a chandelier in your house and you observe the kind of shape those crystals make. Well, we can use polynomial functions to model things like crystals in a chandelier. So if you observe the diagram we have on the right here, um, the it's a mixture of functions, polynomial functions, with x-intercepts of -3, -1, and 5. But they're just kind of some of them are stretched a little, some of them are stretched a lot, some of them are stretched a whole lot. And we can create these patterns by taking polynomials with the same zeros and just changing the stretch, that leading coefficient, that coefficient that stretches the function vertically. In your grade 11 course, you actually talked about scenarios like that, but you only focused on quadratic functions. So in this lesson, we're going to talk about families of polynomial functions in general. And it's going to just basically build on what you did in your grade 11 course. So as a bit of to start off things with a bit of an investigation, I've given you guys two sets of polynomials, and I want you to make some connections between the functions, their actual equations, and the graphs, because obviously in each group there's similarities in the equations themselves, and when you graph them as well, there's going to be similarities in the graphs. Just seeing if you can pick off those similarities. So open up Desmos. I would suggest just graphing all 6 of Group A at the same time, and then separately graph all 4 of Group B at the same time. See what you notice. So I suggest pausing the video right now and doing that. And unpause when you're ready, because I have the graphs right here. So hopefully you took the time and had a look. But what we see from Group A is something that should be consistent with your grade 11 course. What you sketched in Group A is actually a family of quadratic functions that all have the same x-intercepts or zeros. And from our earlier math courses, looking at the equations, since they all have a factor of x minus 1 and x plus 2, we understand that each of those functions will have an x-intercept at 1 and -2. And then we know that the leading coefficient stretches the quadratic function vertically or compresses it. It also allows for reflections. But each of these graphs, no matter what that a value is, no matter what that transformation is, goes through those zeros of -1 and 2. And we observe similar behavior when we look at a family of polynomial functions. So all 4 of these functions from their equation, we could see, okay, there's going to be an x-intercept at 1, -3, and 2. That's true for all of them. We know the leading coefficient changes the end behavior. It might stretch the function or compress the function, or reflect it as well. And that's exactly what we see in the graph. That all those graphs have x-intercepts of -3, 1, and 2. It's just they vary in their end behavior and whether they're stretched or compressed. So what you saw there is a family of functions. But now we're generalizing to polynomial functions, whereas in grade 11, you only talked about families of quadratic functions. A family of functions is a set of functions that have the same characteristics. And we say that polynomial functions with the same zeros belong to the same family. And what we noticed from our little investigation is that the graphs of polynomial functions that belong to the same family have the same x-intercepts, but of course, because they are stretched or compressed or reflected, they have different y-intercepts, right? All their y values are different. Of course, if one of the x-intercepts is 0, 0, since that point is invariant under a transformation, they would stay at 0, 0. The y-intercept would. What does the equation for a family of polynomial functions look like? So if you're describing a family of polynomial functions with a certain amount of zeros, doesn't matter how many, the equation for that family is y equals some leading coefficient and then as many factors as necessary to account for all the zeros. So just off the top of my head here, make up a quick example. Let's say we want to look at the equation for the family of polynomial functions with zeros of, let's just say 1, 2, 3, 4, and just to be different, let's use 6. Well, that equation would look like this. So we know you would have, for each one of those zeros, you would have a factor that corresponds to that. We know that from our first unit, x minus 6. But of course, there's many different polynomial functions, so it would have those 5 zeros. What can be different is that value of the leading coefficient. So there's an example for you guys on what the equation of a family might look like. And we're going to do a few examples finding equations for family of functions, and then maybe given a specific point, single out a member of that family and find a specific equation. I believe you guys will find today's lesson to go by quick, but let's see. So for this example, we're going to look at a family of quadratic functions. So this probably is going to be review, or kind of should feel like review. So we're looking for the family of quadratic functions with zeros of -3 and 2. So let's do the family first. So we know that the family is going to look like this. Y equals, and we're going to use, in this one, we're going to use k for our value of our leading coefficient. We know that the function looks like this. Y equals k, x minus 2, x plus 3. For b, the equations of two functions, you just pick two values of k. It doesn't really matter. So I can list a few of them. You can choose what you want. You could let k be equal to 1. You could let k be equal to -1. That one would open down. You could let k be equal to 10, any number you want, really. Or 0.5, like, hopefully you guys get the idea. Every single one of those graphs would have x-intercepts at -3 and 2. Some would open up, some would open down. I'm just drawing some rough sketches here. Some would open down, some would open up. Might just get a different color. You know, you might have one that opens up, a little more stretched out, just to give you an idea. Again, those two ones I graphed, they're just rough sketches of members of this family. They very, very rough. They don't match any of the equations I listed. But in part C, we're going to pick out the specific family member that goes through the point 1, 4. So I'm just going to get a third color here. And we go through the point 1, 4. And due to some symmetry, it should also go through -2, 4. And I don't exactly know where the vertex is, but this parabola would look something like so, roughly. So as we proceed through part C, we're expecting to find a leading coefficient that's negative. Exactly what value will it be? Well, let's find out. And actually, I think I have space on my next slide. Yeah, I do. So you guys will have this all in the same slot on your lesson sheet. But yeah, let's do C. So what we have so far is that our family of functions, y equals k, times x minus 2 times x minus 3. And our strategy that you guys would have used in grade 10 and probably grade 11 when we did these kind of questions too is that we sub in our point, right? We know that the y value is 4 when the x value is 1. And this gives us an equation that we can solve for k, not a very complex one. So that's negative 1 times negative 2, which is positive 2. Negative 1 times, I was like, why am I getting, I was expecting a leading coefficient that was negative, but I got positive. That's because I did a copying error. Our family is x minus 2x plus 3, so that should be negative 1 times 4, which is negative 4. That's better. And so we get a value of negative 1. And so the equation of that specific family member with those zeros that go through that point is y equals negative x minus 2, x plus 3. So we wrote the equation for a family, and given a certain point, we picked out a specific family member that passes through that point. This was with a quadratic function, probably review from grade 10 or 11. Let's do an example using the same ideas with the polynomial function. Specifically here, we're going to do a cubic function. So we have zeros at negative 2, positive 1, and 3. So that family of functions will look something like, it's a very rough sketch here, but, that would be in the family. And maybe I'll do one that opens down, maybe a little stretchier, a bit higher, something like that. I guess it should go down like this. Just two examples, but let's, and again, just rough sketches. Let's mirror what we did in the previous example. So for A, the equation of this family, y equals k, any leading coefficient. And then we have, because of our 3 zeros, we have 3 factors, x plus 2, x minus 1, x minus 3. And for B, again, it's just choose. I'm not going to write down more than 2 here. You just pick any k value. K equals 1 is an easy one. Let's choose 7 in honor of the greatest Raptor of all time, Kyle Lowry. X minus 1, x minus 3. Just for 2 examples. And let's find here, we're looking for a specific family member. And I'll just draw this in red. That passes through 0, negative 15. Now, we're actually going to do let's actually do D first, just to get a rough idea of what that one will look like. So clearly, it's one that opens down, and it's maybe a little bit stretchier than the previous one. So it'll go up a bit higher. We're making a rough sketch here, right? So something like that. This guy in red, this will be the equation from C. For the guys from part B, I drew the one in dark blue could be a fit for if k is equal to 1, and then I might just actually write that just to sort these out. So k equals 1 for a k value of 7. Might pick one more different color here. Let's see how orange fits. So k equals 7 should be very, very stretchy. So it'd be like maybe even higher. We don't know for sure. Just making some rough sketches, like something like that. That would be if k equals 7. And then, maybe I'll just add a third for part B, just for completeness sake. I'll add a third equation here because I made one that has the one I drew in green, which will have a negative leading coefficient because of the end behavior. So maybe I'll just pick negative x plus 2, x minus 1, x minus 3. And then I'll label that on my graph with green. K equals negative 1. And right now, for part C, we don't really know what the K value is for the graph in part C yet. But we expect it to be negative because of the end behavior of this cubic polynomial. So let's go to some space where we have to work. Well, I'll go to some space where I have to work. You guys should still have some space on your lesson sheet. And yeah, let's get after part C. So the equation or family, x plus 2, x minus 1, x minus 3. Old habit, used a there for the leading coefficient. Ultimately, it doesn't really matter what parameter you choose. And our strategy is always the same. We plug in a point. This time we know the y-intercept has the coordinates 0, negative 15. So we get negative 15 when we plug in x equals 0. And then we just got to work this out. 2 times negative 1 times negative 3, which gives us 6. So k is negative 15 over 6, which works out to negative 5 over 2, or negative 2.5. So it's totally fine to use a decimal here. So we got C done. So the equation is y equals negative 2.5, x plus 2, x minus 1, x minus 3. All right, and we've done D. We did D on the previous slide, sketched a few graphs. Okay, maybe actually just to complete that, maybe I'll just add in red. We actually did find out what that K value was. It was specifically negative 2.5. All right, so let's continue. All right. So we're going to do, because not all polynomials have rational roots, where the root is an integer, or say like a fraction, like a half or 5/3. And that's no surprise to us from your work earlier with the quadratic formula in earlier grades. Not every root solution to equation gives you a nice tidy value. So here we're actually going to find an equation for a family of quartic functions with some very specific zeros. So we have zeros at plus or minus 1, which will kind of, the factors there will be kind of obvious, x plus 1, x minus 1. But what kind of equation would give rise to roots of 2 plus root 3 and 2 minus root 3? Well, we're gonna have a look. So to start off, we're going to set up an equation for our family of functions. So it's going to look like this. We're just going to proceed as usual. Y equals k. So we have zeros of plus 1 and minus 1. So we'll have 1, and minus 1 gives us a factor of x plus 1. And a root of 2 plus root 3. Well, what's that going to look like? So it'll be x minus 2 plus root 3 and x minus 2 minus root 3. And that's what our family looks like. Now, that is correct, but we can clean this up a little bit. I'm going to show you guys how. So first step, I'm just going to clean up those brackets that have kind of a nested layer of brackets in them. So the first one, I'm subtracting 2 and I'm subtracting root 3. So x minus 2 minus root 3. and then I have x minus 2, and I'm subtracting negative root 3, so plus root 3. And we're going to use a special pattern that you guys learned in grade 10. We're actually going to make use of our difference of squares pattern here, because we'll notice we actually have there's actually kind of two differences of squares in our work here. Remember, a difference of squares a plus ba minus b. You can write more simply as a squared minus b squared. So like those first two, maybe I'll just underline them. I'll use green maybe for this one. Here x minus 1, x plus 1. Hopefully at this stage in our math careers, we're pretty okay and convinced that, oh yeah, I can write that as x squared minus 1. Now, the next one, we can also think as a difference of squares. And I'm just going to get a separate color here. Maybe I'll use red. So if I kind of pair these off, I have like x minus 2 minus root 3 and x minus 2 plus root 3. It kind of also fits the bill for a difference of squares. I can write those final two brackets like so. I can write that as x minus 2 squared minus root 3 squared using that special pattern. And this just allows us to make some simplifications and actually get our quartic polynomial with integer coefficients. So we have x squared minus 1. We can clean up this bracket over here. X minus 2 squared is x squared minus 4x plus 4. And the root of 3 squared is just 3. Subtract 3. And we get x squared minus 1. And finally, x squared minus 4x plus 1. We are going to apply the distributive law, and let's just clean this up. Again, let's get a quartic polynomial, an x4 term, an x to the power 3 term, an x squared term, a linear term, and a constant term. So we have 6 multiplications we're going to do. I'll do one step showing those 6 multiplications, and then one more step kind of cleaning things up. So we have x to the power 4 minus 4x cubed plus x squared minus x squared plus 4x and minus 1 times 1 minus 1. And then I'll do some collecting of like terms. Interesting that the x terms kind of divide out. We get k x to the power of 4 minus 4x cubed plus 4x minus 1. And that equation describes all quartic functions that have zeros of 1, negative 1, 2 plus root 3, and 2 minus root 3. So just a good little exercise on when a polynomial function has irrational roots. We can still come up with an equation for it. It's just that it might not be as clean as the previous example where we had integral factors like negative 2, 1, and 3. In this case, it didn't make a lot of sense to leave it like we had up above. It made a bit more sense to make use of our difference of squares pattern and kind of clean it up into something that looks, and obviously I would argue that our final form here looks a lot nicer than what we had originally. All right, let's get going with B. We're going to pick off a specific member of this family. So I'm just going to recopy what I had. So I had k x to the power 4 minus 4x cubed plus 4x minus 1. And we'll just apply our usual technique. We'll sub in x is 2, y is 18, and solve for k. So 2 to the power 4 minus 4 times 2 cubed plus 4 times 2 minus 1. Let's see if this gives us a nice whole number for k or what? So 16, I might just do this in a couple steps. 16 minus 32 plus 8 minus 1. Negative 16 plus 8 is negative 8. Okay, that gives you negative 9. And yeah, we do actually get a nice round number for k. K equals negative 2. And we've got it. The equation is y equals negative 2 times x to the power of 4 minus 4x cubed plus 4x minus 1. But we might write that as, just by distributing the 2, negative 2x to the power of 4 plus 8x cubed minus 8x plus 2. So that's pretty cool. That is the specific unique quartic function that has zeros at 1, negative 1, 2 plus root 3, and 2 minus root 3, but also goes to the point 218. All right. One last kind of question we're going to do together. And you guys, we already kind of have experience doing these kinds of questions. We're going to find the equation for this quartic function. It's just the same questions we've been doing, but here we have a graph. So here we can see this quartic function goes through the point negative 1, looks like negative 6 by the scale. And we can see the zeros, negative 3, looks like negative 1/2, positive 1, and positive 2. So we'll proceed with our usual pattern. We start with the family, right? So y equals k. So we have a factor of x plus 3 because we have a 0 at minus 3. We have a factor of, we have a 0 at negative 1/2, which is going to correspond to a factor of 2x plus 1, right? That's what makes negative 1/2 is what makes 2x plus 1 equal to 0. And we have a root of plus 1, and we have a root of plus 2. In this particular problem, doesn't make a lot of sense for us to expand. That's just a lot of work for little return. The last one, it was useful because it got rid of those radicals and gave us nice integer coefficients. Okay, let's use our strategy to pick off a specific member. We're going to sub in negative 1, negative 6. So y is negative 6. X is negative 1. 2 times negative 1 plus 1. I see what I'm sure some of you guys at home were getting sweaty, getting nervous that I wasn't going to catch this. That should be x minus 1 and x minus 2. And the reason I caught that is because when we plug in minus 1, if you add 1, you get 0, and the k value can't be 0. So I had kind of alarm bells going off in my head as I was doing it. And that's okay. That's just part of doing math, making mistakes. But just, being aware when things aren't working out, just having that self-awareness to be like, oh, I must have made a mistake earlier on. We caught it. No big deal. So that's 2, negative 2 plus 1, negative 1, negative 2, and negative 3. We get negative 6. 3 negatives, that's negative 4, that's negative 12 times k. And so in this time we get a fraction value or a decimal value. Works out nicely to 1/2 or 0.5. So let's just use 0.5. That's fine. We got our equation. Y equals 0.5, and then we'll just keep it in factor form here. X plus 3, 2x plus 1, x minus 1, and x minus 2. I don't know, why did I write y equals 0.5? Mix those two up. K is 0.5. And y equals, geez Louise, we're on a roll this lesson. So y equals, there's our equation. All right, so what should you guys be able to do? Should be able to write the equation for a family of functions and given another point, be able to narrow down and single out a specific member of that family and find the equation of that family. We should also be able to handle situations with irrational roots. We can still find the equation for a family of functions. We just may have to make use of this difference of squares pattern. What's up next, guys? So, in our last lesson, we solved polynomial equations by setting each factor to zero and solving. But what we're going to do is, in our next lesson, we're going to solve polynomial inequalities, where we might be concerned with when a certain polynomial is above zero or below zero. So we'll talk about strategies for solving those inequalities. In the meantime, some suggested practice for you. And again, I'm just being consistent with this message. Practice as much as you need to. Nobody's holding your hand or forcing you to do practice at home, but you should in order to master the material. I'm not trying to overwhelm you with all these questions. I'm just trying to give you as opportunity to practice as much as much as you need, as much as possible. So maybe do every other question, maybe do each question and do a couple, 2 or 3 parts from each. Ultimately, you guys know you the best. So in the meantime, guys, hope you guys are staying well. Please reach out if you need anything. Stay well. We'll see you soon.